One quick reminder that drafts of your Wikipedia articles are due today by midnight. And if you have any questions, please see me or the TAs sometime today. And if you haven't yet gone in to use Sandbox, I would recommend doing that ASAP because it does take some getting used to. And myself or the TAs would be happy to help. But the closer it gets to midnight, the harder it is to be able to help you with that. And so at this stage, you can either submit it as a Sandbox link, which is recommended, or you can write it up as a Word document. Either is fine. But I would recommend, as soon as possible, just getting used to the Wikipedia interface. Okay, any questions on that before we jump in? All right, very good. So we'll start out by just finishing the final problem of the day from last class period's worksheet. It may be an example that you've seen in another class. I'm not sure, but this is a common, I think, example because it's illustrative of some interesting reactivity principles. So this is, if you pull out your worksheet, this is an example from the Wall Laboratory in their studies of synthetic efforts towards various strychnose alkaloids. And so last class we covered the venerable Mizuroki-Heck reaction, and one might expect, based on what we learned in class, that this reaction would proceed via the common sequence of oxidative addition, migratory insertion to make an alkyl palladium, and then in that case there would only be one hydrogen atom on the carbocyclic ring. It could eliminate to give the product labeled as not formed, but that's not what's observed. The connectivity is different, so let's take a minute to think about that if you haven't. Quickly discuss with your neighbor, and then we'll reconvene as a group to discuss it. Sorry. Yeah.
When else it goes through, you move the plate to the Engle position. That's the problem. Yeah. But if you move things back to reactivity, you would expect exit products. Yeah, the product is. But it's the end term. Like it's the structure of the product.
Okay. Yeah. That's
But then I feel like the whole thing is like this. The Engle's like this, and this member is like this. I think it's also oriented, so I'm not sure if you can find like that.
Okay, let's put some structures on the board. Xiaochun whether you can get us started and see where we go.
Next thing is first go with the oxidative addition to the carbon ion.
Okay, that is a good place to start.
If anything,
Why would you say that?
Xiaoxun, what do you think? Zhang is on deck, sounds like. He's ready to help at any point. Okay, what do we think now?
maybe do the insertion of the olefin in the lower part.
Okay, so you have two, so you're wanting to do migratory insertion,
Yeah.
and you have two choices. And ultimately, the bond that's going to be formed is here. And so if you do that, then you're going to get an intermediate with a CC bond here and a carbon-palladium bond here. And I'll tell you that the transition state for that is going to be quite strained, which probably you figured out as you were sketching it. Not unreasonable, but that would be the most direct way to get to this product. Form this bond, put palladium here, beta hydride eliminate out that way. But in practice, I think that's not the most likely outcome. Zhang, what do you think?
I had an idea. Maybe the carbamate is participating.
Okay,
It's
I like that idea.
It's like the palladium's on top and the carbamate's on the bottom. So maybe there's like some participation where like it assists the reductive glutination of that final group onto that desired carbon.
Okay, so I like this idea that this could serve as a coordinating group or a directing group. So let's go ahead and draw out that intermediate. And I'm not, just in the interest of time, I'm not going to draw this out in 3D, so you're going to have to take my word for it that this doesn't look so horrible. When it's actually drawn out. And this is participating, you said somehow in something.
Yeah, I guess there's like some type of equilibrium that forms somehow, maybe, possibly.
Anyone, any volunteers from the audience want to jump in?
You have to do some kind of nucleophiles chemistry with the carbamate.
With the carbamate.
I don't know, just a random.
So you're saying here it could coordinate to the alkene and undergo some pyruvate acid activation. The carbamate could participate, and then.
Or can the olefin just come in again? And that you
I like that. What do you mean? Come in again.
So that
React further with the...
Yeah, it reacts
okay.
further with palladium, so that you... It's like a swap, kind of.
Okay. You're on to something here. And so at first glance, what I'm going to draw is you're going to just say, well, this looks super esoteric, and I'm not going to encounter this very commonly in my work, and you might not. But anytime, or a high percentage of the time, when you have an alkenyl halide and you're doing hecatype chemistry, you can have this kind of rearrangement. And so for those of you who've read like Scott Snyder's recent paper in Nature, they invoke this as well. So this is really nice proposal. I just pulled up the reference here on my phone so I don't get it wrong. So good thinking here, Zhang. So it's a little hard to visualize what just happened, but essentially this alkyl palladium can now re-engage with the alkene in a heca-type pathway, so it will undergo migratory insertion across this alkene to generate this cyclopropane with now a carbon-palladium bond at the alpha position. As you might imagine, this is happening reversibly, so migratory insertion, beta-carbon elimination. But a productive pathway can take place if rather than beta-carbon eliminating to give this carbon-palladium bond, you can beta-carbon eliminate to give the opposite one. And so that sets us up to then proceed via the pathway that Xiaochun suggested all along, which is the one where here. And then beta hydride elimination as proposed earlier. And so as I said, at first you might think, well, I'm never going to see this rearrangement again. But again, it's quite common in these sorts of cases, alkenyl halide, particularly intramolecular alkenyl halide migratory insertion that sets up a reversible cyclopropane formation, and that can be a useful and enabling stabilizing element. And then the other key point here is that emphasizes that directing substituent perturbs the pathway selectivity of this overall process. So without this, the system is prone to the predicted pathway, where after you undergo syn migratory insertion here, you can take advantage of this syn periplanar CH bond for the classical beta elimination pathway. So some I think useful lessons to take away from that example. Okay, so now let's shift gears slightly to focus on the main thrust of today's class, which is on catalytic Allylic substitution reactions. And so I will introduce this topic by first taking a step back and thinking about nucleophilic attack on carbogenic fragments coordinated to metals. And so at the beginning of the previous class, we discussed the Davies-Mingos rules for nucleophilic reactivity of carbon-based ligands bound to metals, and one manifestation of that was in the alkene functionalization reactivity that we covered last class. And so a related topic related reactivity paradigm are nucleophilic attack to allyl groups bound to metals. And so I've depicted the sort of general stoichiometric version of this elementary step here, where a metal-bound allyl fragment is electrophilic at both of the terminal carbon positions. And so a nucleophile can attack most commonly via an outer sphere pathway, but it can also engage via an inner sphere pathway. And even though this reaction looks somewhat different than other types of reductive eliminations we've covered in class, it is formally a reductive elimination because the oxidation state of the metal is decreased by 2 and a vacant coordination site is created on the metal. Perhaps unsurprisingly, the reactivity trends follow what one might expect. More electron-poor metal accelerates this elementary step. And so charged species, cationic charged species are more reactive than neutral anionic species. And allyl fragments can be viewed as a special type of alkyl metal or sigma alkyl metal species. And so in comparison to other sigma organometallic complexes that one might encounter, allyl and acyl metals are unique in the sense that they have low-lying LUMOs that enable nucleophilic attack, whereas aryl, vinyl, or alkyl metal species do not. And if one thinks about the charge distribution of these complexes, they actually typically have partial negative charge on the carbon fragment. This just goes back to what we covered very early in class about electronegativities. And so attack on these fragments is disfavored just due to charge arguments. You'd have a partially negative species attacking another partially negative species. And so allyl fragments, as well as acyl fragments, which we've seen elsewhere in class, are somewhat special in terms of their reactivity. Allyl metal species can exist in two forms, the eta-3 form and the eta-1 form. And the equilibrium, the speciation in solution between these two forms can be affected by all the things that you would expect. The ligand identity, the identity of the metal, the identity of the substituents on the allyl group. But one that is useful in terms of reactivity is that, and sort of catalytic cycle design is that with higher amounts of ligand loading, the system can be driven towards the eta-1 form. And so in cases where populating this species is desired, for example, if one wants to epimerize a stereodefined allyl metal, then adding ligand can be a useful way to achieve that. And then so these two organometallic tautomeric forms can react with nucleophile in different ways. So the eta-1 form can react via an SN2' type pathway with soft nucleophiles, whereas the eta-3 form will react in this outer sphere pathway. And so there are different, we'll get into this in just a minute, but I'll just make a general comment now. So there are different metals that are used in catalytic Allylic substitution. Palladium has probably been the most, maybe not, I wouldn't say probably, has been the most extensively studied and has its own sort of unique reactivity trends. Iridium, molybdenum, tungsten, and others have their own group of reactivity or set of reactivity trends, and copper has its own unique set of reactivity trends. So we're going to focus most of today's lecture on reactions by palladium, but it's, of course, interesting and illustrative to compare it to reactivity of other metals as well. So as a warm-up, let's consider problem of the day number 1. So this asks you to predict a reactivity of this molybdenum CP complex, CP Al complex that has a bound CO and a bound NO ligand with a generic nucleophile, generic soft nucleophile. First, to identify the I would say, based on Davies, Green, Mingo's rules, first identifying the fragment, the ligand fragment that is going to be engaged by the nucleophile, and then thinking about regioselectivity of that group, regioselectivity of that addition process. Okay, so take 30 seconds quickly to look at that and think about it. My hint on this will be don't overthink this. Okay, Saul, what do you think?
I think Al is definitely more reactive than CP.
Okay.
It's a fragment reactivity. I think it's going to react by the standard path to put nucleophile on the outer carbon.
Okay, so comparing CP and Al, Saul's saying that the Al is open, CP is closed, so Al is it's going to be much more reactive. I mean, you can either think of that in terms of Davies, Green, Mingo's rules, or just intuitively an aromatic fragment versus a non-aromatic fragment. One's going to be more reactive than the other. Okay, and now the Al fragment can react at either carbon atom. Which would you expect to be more reactive?
I guess trans is the CO.
Trans the CO. And what's your reasoning there?
CO is a better back bonder, so it's stronger trans influence.
Perfect.
That's that point.
I'll draw this with defined geometry just to look there. And this is molybdenum 2+ ox, just so we get used to these oxidation state changes. These are molybdenum 2+, it's molybdenum. Okay, did anybody get anything different than that? Okay, so just writing out those rules, or not rules, but reactivity trends.
The starting complex cationic and the final one neutral.
Let's see. Did I get something wrong? Oh, yeah, you're right. This is. Thanks. I looked at that. Right, linear NO should be +1. Thanks, Tanner. Okay, so attack will occur preferentially trans to the ligand with the higher trans effect. That, I realize, is a bit of circular logic, but let me just elaborate on that. So ligands with strong trans effect tend to be those that are capable of pi back bonding. They also, in general, tend to be a little bit better of sigma donors, if you consider phosphines, for example. And so what happens is that a strong trans effect ligand weakens the bond to the allyl fragment that is trans to the ligand that leads to partial positive charge accumulation at that center, and that determines the kinetic selectivity of how the incoming nucleophile will engage. And then we discussed the difference between attack in an open versus a closed carbogenic polyenol fragment. Good. So we'll see. We'll have other examples discussing the regioselectivity of attack of pi-allyl species. So hopefully these trends will become evident as we go through today's class. So much of what we'll talk about today, as I mentioned, is focused on palladium pi-allyl complexes. I think they're an illustrative set of examples to consider. And so we've discussed so far how metal allyls react with incoming nucleophiles, and it's also important to consider how they're generated. Classically, and what we'll see throughout most of the class today is that they're generated through allyl electrophiles. These include things like allyl halides, allyl acetate, and other allyl alcohol derivatives. And these can react with palladium 0 via oxidative addition. The oxidative addition pathway happens in an invertive SN2 type mechanism. We'll come back to this. And then there are other ways that palladium 2 pi-allyls can be generated. One that's of both preparative and historical importance is this formal allylic CH activation or mode of reactivity where a terminal alkene coordinated to palladium-2, when that takes place, the alpha CH bonds are acidified such that a bound acetate or bound internal base can deprotonate to lead to a palladium-2 pi-al. And industrially, this process is important because it's how al acetate is generated. Propylene plus palladium-2 plus acetic acid. Very efficient, done on large scale. And then there are other less common but also important to think about ways to generate palladium-2 pi-als. So you can do the opposite polarity version of this where you have an al organometallic species reacting with palladium-2. So this would include things like al boron, al Grignards, etc. And then pi-al species can also be generated by addition of the corresponding metal hydride to an allene or a 1,3-diene. For those of you who attended Steve Malcolmson's lecture the other week, this was a commonly invoked mode of reactivity in his chemistry. So the important thing is to know that there are different options and different entry points into this type of intermediate. So now let's consider the catalytic versions for putting these different elementary steps that we've discussed together, and then thinking about guiding principles for how to predict reactivity, selectivity, etc. And so here's just a general depiction of a generic catalytic allylic substitution. You'll note immediately that the reactions affect essentially an SN2 process or an SN2 prime process. And so in comparison to that non-metal mediated reactivity, the advantages here are that you can control regioselectivity, you can control enantioselectivity, and also in general allylic electrophiles reacting with nucleophiles in the absence of metals. Those are often quite messy reactions. And so this chemistry has been developed most commonly with soft nucleophiles. These are defined as nucleophiles that have pKa's below 25. Classical one here is some kind of malonate. And then in terms of the stereochemistry involved, we talked about how the oxidative addition step precedes an SN2 type invertive pathway. With soft nucleophiles, they attack the corresponding pi-al by an outer sphere pathway, so that the overall effect of double inversion is retention. And then one of the things that complicates this picture a little bit is that there are various isomerization pathways that pi-als can engage in. And so it's not always as clear-cut as it might look at first glance, and we'll discuss that as the class moves forward. So some of the historically important reactions I've highlighted one here and another. I was midway through drawing, so let me complete that. Okay, so this early history brings us to the chemist of the day, which probably people can guess. I heard some whispering. Anyone want to shout it out? Trose. I hear Trose from his younger days. Okay.
Yeah, you guys are like all first and quizzes.
So born in 1927, still with us. He's in his 90s now. Educated at Kyoto and did his PhD with Gilbert Stork at Columbia. His main affiliations during his independent career were with initially with a company, basic research lab of Toray, and incorporated, and then in the early 70s he was invited for an appointment at Tokyo Institute of Technology. But for those who are paying attention to the timing, his real flurry of arguably the most impactful papers were in the mid to late 60s at Toray. And then later in his career, he moved on to Okayama University of Science and Technology. And of course, well known for really driving the field of organopalladium chemistry. Particularly the development of Allylic substitution reactions. Which now I think anytime we're thinking about, we discuss metal-mediated Allylic substitutions, the names Tsuji and Trose are on our mind. Okay, so in 1965, Tsuji reported this landmark paper. And for those who are thinking about the timeline here, this was the same year, almost immediately after the publication on addition of malonate nucleophiles to palladium-2 COD complexes. So remember that the inspiration for that work came from thinking about how to generalize Docker-type reactivity to other classes of nucleophiles, and now he's generalizing further to other classes of reactive organometallic fragments. So he found that treating palladium allopalladium chloride dimer with the same nucleophile we encountered earlier, just deprotonated diethyl malonate, DMSO ethanol, led to this formal alpha allylated product, along with palladium 0 precipitate, which can be observed as palladium black, sodium chloride. And so this this reactivity was then quickly developed by some of his coworkers at Toray, as well as another research team at Union Carbide into a catalytic process. But it took the better part of a decade for the full potential of this to begin to be realized. And so a pivotal publication came out in 1973 from the Trose lab. And so during the course of total synthesis efforts, the Trose lab was working with this class of allyl palladium chloride dimers, which, interestingly, this is an interesting part of, I think, chemical history. These, in turn, are actually accessed via CH activation. And so they could isolate these, characterize them, and then when they subjected them to Suji's reaction conditions, they found that the reaction was dramatically improved by the addition of multiple equivalents of triphenylphosphine, and in some cases the reactions were essentially instantaneous. And so, as we've seen in other types of reactions, finding the right ligand is the key to unlocking the full potential, and that was the case here. Almost immediately after this discovery, in fact, the same year, the Trose lab recognized that because this reaction creates a new stereocenter, or depending on which isomer is obtained, it can create a new stereocenter. It would be powerful if rendered enantioselective, and so this started what became a 20-year odyssey to find the right ligand set for palladium catalyzed Allylic substitution reactions. Their initial version was this chiral at P ligand. And so I think we've seen this before in other types of reactions where often the starting point is some chiral at P version, and then the reaction is developed further. And the culmination of their efforts was the identification of this family of chiral 1,2-diamine derived ligands, which we call Trose Ligands. And this was first report of this ligand family was in the early 90s. And so some of the design principles here I'll just sort of describe qualitatively were that if one thinks about where so if one considers this intermediate and ligands that are out here, then the ligands are coordinated quite distal to where the new stereocenter is ultimately going to be formed. So part of the idea here was to have ligands that have relatively wide bite angle. It can span quite a large distance to give with the hope that we would be able to project into the path of the incoming nucleophile. And we'll conclude with some additional discussion of enantioselective catalysis. So for electrophiles in this chemistry, here are some general reactivity trends. The most reactive are these Allelic carbonates, followed by Allelic phosphates. And one of the advantages of the Allelic carbonates is that they have an equivalent of base embedded in them. So upon oxidative addition, they lose CO2 to generate methoxide anion. And so as you see in the catalytic cycle here, I guess I don't have the drawing, but deprotonation of the nucleophile is an essential part of the chemistry, so these are advantageous because you don't have to use exogenous base. This I'll maybe draw over here. So with palladium, a very high percentage of the published examples are with soft nucleophiles. And so when in doubt, if you see something, with palladium, you can assume it's going to, and you're not sure, just, I guess, assume that it's soft. And I think that with palladium, at least, a very high percentage of the successful enantioselective versions are all with soft nucleophiles. It's been much harder to develop versions that work well with hard nucleophiles with palladium. So if one takes a enantio-enriched Bial species, and with soft nucleophiles, you get inversion. In this case, both of the regioisomers are observed. Combine 86% yield. this implicates stereoretention. And so the opposite situation is with the so-called hard nucleophile. This is something, any group that has a conjugate acid with a pKa above 25. And I think classically these are often organozincs, grignards, etc., but they can also be carbonyl compounds that just have low pKa's, for example, simple ketones. And so with hard nucleophiles, the reactions proceed. Let's say a reasonable mechanistic proposal is that the reactions would proceed via an 801 intermediate. And soft nucleophiles would proceed classical 803 intermediate. And so in terms of general reactivity trends, inversion for soft, and then I'll just clarify that this leads to overall retention in the catalytic version. Retention for hard. And with palladium, tends to form the product corresponding to addition at the terminal position. So, or more generally, the less substituted position. And this can be affected, as one might expect, by ligand. Okay, let's now turn to problem of the day number 2, which will serve as a springboard for a discussion of regioselectivity trends. So here we have a diaryl substituted allylic acetate. The design of the electrophile here allows for systematic variation of the electronic properties of both aryl groups. And the question asks you to think about, from the reaction drawn, what two products will be formed and which you would expect to be the major product. take a minute to think about that. Discuss with your neighbor. And we'll discuss it as a group. Okay, let's start out with the easy part. Max Palkowitz, what are the two products that will be formed in this reaction?
I guess a mixture of regioesters where we have alkylation either next to the nitro group or the oxy.
Okay. This is nucleophile. So this is nucleophilic at the alpha carbon between the two pseudocarbonyls. So this is a CC. Maybe I'll just draw this as a C clear. Okay, Max, and which one do you think would be the major product?
So I feel like I can make an argument for both, but it would probably come down to whatever site on there can best stabilize the positive charge when bound to the age rebound to palladium.
Okay.
So I guess that would be, I kind of want to say the epoxy. Next to the epoxy.
The major product would be this one. Okay.
But at the same time, I could also reason why the other one would be major as well.
Okay. Anybody else want to offer a rationale and explanation?
The methoxystyrene product, I guess the left one, is a better ligand for palladium.
Okay, so you're making a thermodynamic argument.
Yeah.
But I think that in this case,
I'm just saying that's a thing. I'm not saying that would override.
sure. I think in a stoichiometric experiment where the process was likely to be reversible, and you can imagine it being controlled by thermodynamics. Okay, so one way to think about this is if you consider the two. This isn't the only way to think about it, but remember that Al groups are essentially Al anions bound to metals. And so if you thought about, based on this substitution pattern, which of these resonance forms was more likely to predominate and govern reactivity, probably everybody, or I guess I shouldn't make any assumptions. But that okay, let me back up this explanation because I realize I'm going to confuse everybody. Let's just draw out the actual intermediate. So this really will end up coming down to which of these two sites is going to have partial positive charge. If you think about it, it would stand to reason that the more strongly electron withdrawing group is going to have a stronger dipole and lead to more partial positive charge buildup on this position than the more electron donating group. And if you want quantification for that, you can look at the handout that shows the C13 NMR shifts of this series of complexes. And then one will see that this carbon atom is shifted downfield compared to this carbon atom. And so based on that argument, nucleophilic attack happens preferentially proximal to the electron withdrawing aryl group.
So it's to do with it's like a lower energy lumo site.
A lower energy lumo, you can think
It's
of it
not
that.
really a thermodynamic.
It is kinetically governed selectively. Are there any questions on that? And so on one of the other tables in the handout, you will find another useful set of NMR measurements that shows you how different ligands so I'd encourage folks just to spend a minute thinking through this and making sure that everything's clear in your mind. How, as the identity of L1 and L2 change for a common L fragment, how the C13 NMRs shift. And based on the discussion that we had before, if this is a higher trans-influenced ligand, would you expect this to be shifted upfield or downfield? Someone can just shout out. Vincent, what do you think? Higher trans effect ligand. So let's consider an extreme case like a phosphite. Higher trans effect, we said, should be electron withdrawing off the metal, and so should lead to partial positive charge buildup in general in the owl fragment, but particularly trans to it. So you'd expect that to be shifted downfield. And so I think that these two principles also, when viewed through the lens of the substitution pattern and the steric effects of that substitution pattern, really allow one to make educated predictions about the site of the regioselectivity of these fluid substitution. And I think this also, and at least in a qualitative sense, this framework allows one to think about how, particularly in cases where you're doing allelic substitution on like a terminal Al fragment, why it might be advantageous to have electronically unsymmetrical ligands, like the common PN family of ligands. Okay, any questions on that? So in the remaining time, I'm going to give an overview of what are really large topics in the literature. And so I won't do these justice, but I do want everyone to just be aware of what's out there and direct you to the appropriate references so that you have the opportunity to read more. So historically, most of the work in Allylic substitution has been done with palladium, but particularly in the last 20 or 30 years, there's been also extensive work done with other metals. And probably outside of palladium, the two that have been most popularly studied are iridium and copper. So let me now just paint a picture about the general reactivity and selectivity trends with these other metals. So with molybdenum, tungsten, ruthenium, most non-palladium metals, the reactions are branched selective. And as you thumb through, or as you page through ASAPs, you'll recognize that there's always no shortage of publications with chiral iridium catalysts, with various nucleophiles in this type of regime. The linear products are favored predominantly with palladium. There are also nickel. Nickel pile chemistry is a little bit different because depending on the oxidation state of nickel, it can actually be nucleophilic, but we won't get into that. And then there's also been a huge amount of work done with copper, and copper stands apart a little bit from all of these metals because, and because of that, it's actually its own chapter in the Hartwig textbook. And what's different about copper, I mentioned with palladium that hard nucleophiles, particularly enantioselective reactions with hard nucleophiles, have not really had a lot of success. With copper, that is not the case at all. And researchers have found a great deal of success using copper for this family of nucleophiles. Many contributors to this area of research, including folks like Alexakis, Hoveda, many others. They typically give branched products. Mechanistically, they proceed via a pathway that is, I analogous to what I've drawn here, where the first step is inversion and the first step is invertive and the second step is retentive, so the overall process is invertive. Robust, very enabling enantioselective methods. Say it again. Sorry, this is a robust enantioselective method.
And just about that anti.
Well, it's overall invertive, and another way to describe that is to say it's anti-selective, meaning that the nucleophile is installed anti to where the outgoing leaving group is. So thanks for asking that clarifying question. I'll just over here. Metal pials, as I alluded to, are capable of undergoing isomerization. This is of central importance to enantioselective methods. And so within a single metal pial fragment, if it's able to stay in its A-3 form, then it is configurationally robust and it will not undergo, if it's stereo pure, it will not undergo racemization. But there are pathways that these can epimerize, so I'll draw those out now and leave it to you to think about implications in asymmetric catalysis, and we'll have one example of this on problem of the day number 3. So A-3 pials, as we mentioned, can tautomerize to the A-1 form, and this can be favored by addition of exogenous ligand, or promoted, I should say, by addition of exogenous ligand. So with terminal L fragments, terminal L fragments, that provides a means of obtaining either of the two potential mirror images of the pial from a single enantiopure Allelic leaving group species. In the context of enantioselective catalysis, what that means is that if the kinetics are on your side, you can go in with racemic starting material and through a dynamic kinetic asymmetric transformation get out an enantiopure product. I basically just wrote down what I just said in a different language here. And so that's the terminal case. You can also consider the internal case. And probably you immediately recognized that the epimerization process for the terminal case hinges on this ability to make a racemic eta-1 pi owl. But in an internal case, when you undergo eta-3 to eta-1 tautomerization, the stereochemical information is transferred to the stereocenter of the carbon-metal bond. As long as R1 and R2 are different. So if they're the same, of course, now this species is racemic. And so, nevertheless, these internal pi owls can also undergo isomerization, and that can take place via a bimetallic intermolecular process where there's essentially al group transfer, kind of like vaguely analogous to halonium transfer from one alkene to another. So I think with these different isomerization processes, it can become a little overwhelming and in terms of predicting possible reaction outcomes. So I guess my general rule of thumb would be, as you're looking at these systems, try to keep it as simple as possible first, and only if the simplest framework doesn't lead to a result that makes sense, then start bringing in some of these more nuanced insights. Okay, let's turn to problem of the day number 3 with our remaining time. Problem of the day 3 asks you to consider one step of what is a multi-step total synthesis of the natural product bruconiatine G. This synthesis actually involves multiple allelic functionalizations. And so this is the first one. I'll draw it out. So one of the inputs is this racemic. Note that this is racemic. Allelic epoxides. Phthalimide is the incoming nucleophile. Catalytic palladium 0. Trose ligand. Okay, Cheng, let's get us started with this.
So first, plate 0 will insert to the oxide to make the pile species.
Okay. So these allylic epoxides also bring their own base, which is a convenient feature, can be a convenient feature. And because the starting material is a racemate, you will generate 2 diastereomeric pile species, right? Okay. So now what?
And then the succinimide will I guess it's soft base. So we'll handle S25 to give you 1 for dye substitute.
Okay, 1 for dye substitute. And I'll give you a hint by encouraging you to look at the structure of the product, the natural product, and think about where this is going to map into. So in this case, we get the 1,2 functionalized product. How would you? What is the origin of that selectivity? It has something to do with the use of the Trose ligand, and I would say, just in terms of the design of the problem, because we're using chiral ligand, it would make sense that the product is going to be enantioenriched. But this only accounts for half of your material, right?
Yes.
So what else is going on? Well, we just covered this, that the wrong diastereomer can undergo eta3 to eta1 isomerization. Which provides a means of accessing the other diastereomer and so the overall process can be stereoconvergent. And this is an example of what's called a Dicat dynamic kinetic asymmetric transformation. Maybe some of you have heard this term. This is closely related to DKR reactions, dynamic kinetic resolutions. The difference is that in a DKR, typically there's a polymerization, a racemization catalyst that itself is achiral. in this case, at every stage, the metal doing the action is a chiral catalyst, and so that's the distinguishing feature. And so from this, just in case anybody is interested in synthesis, I'll just provide not all of the details, but want to look into the key step. So they actually use this reaction then a second time. And I think now, hopefully, this will start to resemble the core structure of the tropo. So this is an example of the chiral catalyst in action. In the interest of time, I won't go into all of the different ligands and applications. There are many different types of reactions that can be done enantioselectively with Allelic alkylation. You can consider, for example, a prochiral nucleophile and setting stereochemical information on the nucleophile. You can have desymmetrization versions. You can have dynamic kinetic asymmetric transformation versions. These are summarized on the handout. So I'd encourage you to look at that. And there's also a Trose Chemrev that, at least for the palladium systems, summarizes this quite nicely. With our remaining time, we'll look at problem of the day number 4. So this is a case where the two reaction partners and an allylic substitution are tethered together. I think this example is probably from the Stoltz lab. Is that right? Joe's nodding. Okay. So the first part of the question is about the structure of the ligand, T-butyl Fox. Does anybody want to shout out that structure, or what does Fox mean? Okay, Dongman.
I only remember it has an oxazole.
Oxazoline.
Oxazole.
Yeah. Okay, that's good. Tanner, what did you want to say?
It has a phosphorus with T-butyl group.
Yeah.
That's not quite right, but it's close.
It's T-butyl
Phenol. Yeah, could be there.
Yeah,
Phenol there.
and Tucker wants me to draw a phenyl ring here, and then there's going to be a phosphine somewhere. And so one of the key points, in case it's not obvious, is that this 1,2-amino alcohol is derived from alpha amino acid, in this case from the unnatural amino acid T-butyl glycine. But the valine-derived version of this, which has an isopropyl group here, is also quite efficient. And the key developer of the Fox family of ligand, key developers are Helmchen, Williams, and Faltz. So these are PN ligands. We talked about how it can be advantageous to have electronically desymmetrized, or ligands that electronically desymmetrize the two transpositions in Allylic substitutions. This ligand in this case is a much stronger trans effect ligand, so you'd expect this site to be more electrophilic. Okay, and what is the product? Or let's just do the mechanism and the product together. So anyone want to walk me through what's going to happen here? Okay. Okay, first let me draw this out properly. Okay. Now you have, I think saw Stoltz speak recently. I think that they are entertaining the possibility that this process might be concerted. So in general, it is challenging to form quaternary centers with Allylic substitutions, and so this intramolecular model would be a way to explain why this reaction is so efficient and so selective. And I don't remember off the top of my head which isomer is formed, but I don't think it's necessarily essential. Any questions on that? Anybody got anything different? Okay, that wraps up today's class. Happy to answer any questions. Thanks, everyone.